Tonight we're going to go through a little bit more details of how we think the current favorite concept for the 3847 robot is going to be implemented. We're still working on the idea that we're going to have a elevator and a double jointed arm. Both of these things are mechanisms that we have relatively good and recent experience with. We've built elevators most of the last few years. We've built at least single stage elevators. And the double jointed arm concept was from our 2023 charged up off-season robot that we built to play at Remix and Chesney Champs. And so we have pretty good idea of how those work, and we're able to do, we believe we're confident and able to build them. We're also able to do the software for them as well, and we can also even improve on what we built in the past. So the first thing I want to talk about tonight is how we think we're going to potentially build the elevator that we need to be able to get some of the vertical height necessary to score the level 4 coral and the algae into the net. The plan currently is to use a continuous belt elevator. It'll be similar to the one that was designed by a 111 Wild Staying student and posted before the season started. Most elevators are all pretty similar. They have some sort of motors down here at the bottom. They're spinning and they're able to pull a part of the elevator up. Single stage elevators are very simple. We can kind of look at the CAD for this one. This is a double stage elevator, right? So you have the first stage that moves is here, this bigger box, and then it has a second stage, which is often called the carriage, that moves up and down here. So the elevator concept that we're talking about won't have this carriage at all. It'll only have this first stage, so it's very easy. If you have multiple stages, you have to be able to run the belt in like this sort of like Z pattern here where it goes up and down and back up. But for our single stage, we're just going to run it up and then down fully to here. It'll mount to this stage, both on its up pull is the one that goes kind of up this way, and its down pull. Okay. All right. Sorry about that. So we will go, yeah, so it's a single loop, so it's relatively easy. We don't use everything that they're building into this. We have some things that we use on our belt elevator from 2023 that we liked. And so we'll take some of the things that we liked from there, some of the things that we liked from here, and make a design that we believe will work. So some of the elevator basics are that you need to have your motors and kind of pulling on the belt. Okay. All right. So the motors are in the gearbox here. They're spinning this pulley, and as it moves one way, if it's spinning clockwise to the direction we're looking at it, it's going to pull down on this belt and it's going to pull the elevator down. If it's spinning counterclockwise, it's going to pull this way on this belt, and since it's pulling this side of the belt down, the other side of the belt way up here is going to be pulling up, and that's what's moving this stage of the elevator. And so that's what we're trying to do. But we don't have to send it up again because we don't have that other carriage. So we only have to basically mount to this end. So the belts you use for elevators aren't like the belts we'll use on other systems. They don't come necessarily as a full loop. They're just going to come open-ended is what it's called. And so we'll basically like cut the belt here, and we'll have a way to mount it directly to the side of this tube so that when we pull up on it, it goes up. And then on the down, we'll have the down belt come up here, go over this little pulley here. So if I hide the belt will just come over this. It'll come through, there'll be a gap here, you wouldn't have this block there. And so then you have to have the end of the belt here, And this is what we would use to tension the belt. So we'd be able to kind of like wrap it up in 2023. And what we'll probably do this year is we use an actual like cutoff ratcheting wrench, and it allows us just to wind the belt up and apply more tension. It's because the belt lengths kind of change, they'll stretch a little bit, and so you have to have some way to tension it. In the design in this CAD, they have a few of those things done here. So you can see, like, so here is how they actually mount the belt to the side of the tube. We can kind of look at that. So there's this little cage here, and they just bolt it to the side of the tube, and the belt teeth are sitting inside of this. So we'd be doing something similar here, except we'd be mounting it permanently to the top of our, or to the midsection somewhere down here of our middle stage. Oops, let me put the tube back. Yeah, so we'd be mounting it somewhere down here. It would be permanently attached. And then for their tensioning system, they have it tensioned at the top, but we're going to flip that around and tension at the bottom. And so it comes over the pulley, and they have it kind of mounted here, and they use this cam to tension. So as you turn this, this whole assembly wants to slide to our right, and that pulls on the belt, and it makes it so there's no loose parts or anything, and that allows us to have the motors, as soon as the motor moves at all, the whole system moves. It's not having to like take any slack out of the belt or anything, and you have like the sluggish motion. If you have a loose belt or anything skipping, you don't have the belt being able to like fall off the pulleys anywhere, so you really want to make sure it's tensioned. So instead of this system, we would probably have like a shaft that we're just wrapping the belt around, and we found that that works very well for us. If for some reason it doesn't work, we also have another concept from another team who do post their designs openly the same way we do. And so we could use something like this if for some reason the system we're using and that we like doesn't work. Something like this is also just as good. We'd have to manufacture these plates. It's not that difficult. The other part of the elevator, so that's how the elevator is actually powered up and down. The part of the elevator that actually allows it to like slide up and down nicely and not get jammed anywhere are the elevator bearing blocks. And so that is where we have this setup that Wildstang created. It uses bearing blocks that Rev Robotics released this year. So these pieces right here, let me see if I can, oh, maybe, there we go, we can isolate all the way there. All right, so this part is your Rev Robotics bearing block. It has our larger bearings that ride on the front and back of the tube. So this takes most of the weight, as normally whatever you're actually having the motion on is normally mounted on this face of the elevator. And so you're kind of hanging weight out of it, or it's mounted, yeah, so no matter which way you're using the elevator, it's kind of hanging out over here. And so the whole elevator sort of wants to tip forward, and these bearings are preventing these rails from doing that. So as it's sliding up and down, this bearing and the one on the back are constraining our tube and allowing it to very easily spin up and down. Like, so they spin and it allows it to easily slide up and down. So you can kind of think of it like drawer slides, except turned vertically. They're doing kind of the same thing with these rollers and having them slide up and down. And then you also have bearings on these internal faces that are a little bit smaller. This allows us to keep the gap between our tubes relatively small. In the case of these bearing blocks, we have about a ½ inch. There are some other bearing blocks that give you a little bit tighter packaging, where this bearing is kind of shifted in a little bit, and so you can get about a ¼ inch gap. That can be convenient, but because since we're only doing a single stage anyway, the gap is okay here. It allows for some easier maintenance. It allows us to potentially like have some zip ties or whatever else you need to have in here or something, and nothing's rubbing or catching anywhere. So having that open space sometimes can be a benefit, and we think in this design for this season, it will be for us. And so those we just purchase. They come with the bearings, they come with the hardware. They're easy enough to work with. But you also have to be able to actually hold and run the belt, and so that's where this CAD project comes out very nicely, are these bearing block segments in here that are holding these idler pulleys. These aren't transferring any power, so we call them idlers. The belt's just running over the top of them. And so this is basically just a shaft. There's some bearings here so that they can spin freely and not add any friction or load, cause it to jam or anything. We want everything to spin really, really smooth. And so these bearings can do that. And it's all built into this nice little package. And so if we go and we switch over to the bearing block tab, we can kind of see what this whole thing looks like. And so you, instead of having these blocks, which are often just mounted directly to the aluminum rectangles, that aluminum extrusion that makes up the frame of the elevator, we're instead mounting them to these plates that we'll custom cut. So these are some of the only custom parts of this whole assembly. And so this allows us to have some tapped holes here, so we can just bolt straight in to these plates. It allows it to very easily come on and off. And then you can also support everything, and they're relatively easy to make. They're just flat, so we'll be able to either have, we could cut these on our CNC router, we could cut these on the water jet that we have now. We could also send them out to one of our sponsors or to FabWorks or Send Cut Send or any of the contract manufacturers to do that. And so they're relatively easy and relatively cheap. There's no complex geometry. 2D metal parts are relatively easy and cheap to make. And then this means that we don't have to custom machine any of these tubes. So a lot of the other times people have made this style of belt elevator, you're having to basically, instead of like having this nice little pocket built up for this idler, you're having to machine that hole and that interface into the face of this tube. And that's a little bit more work. It makes it a little bit harder to replace things. If something were to happen to this tube and it got damaged somehow, and it had custom machining in it, you have to have another custom machined one ready to go. Instead of just having some generic 2x1 that we already bring to events, that we already have a lot of, it just allows the elevator to be a little bit simpler to use and manufacture. You're making these simple plates here, and these ones here that actually act as like an L to connect the two tubes together. And so they join everything, and they allow for a very robust, easy to put together elevator that's also easy to maintain and repair throughout the season. And that's really one of our goals for something like the elevator, is we want to build it once and make sure it'll just work all year. We don't want to be having to do a lot of work on it, maintenance on it, unless we have to if something gets damaged or something. We don't really want to be upgrading it. We want it to be reliable and just work every single time, so that we can be focused on the things that actually like directly interact with our game pieces and make those things better through our development time. Some of the other simple things on the elevator, you normally do have to have some sort of crossbar. In this CAD, they use a round one. We may use a flat plate or a bent sheet metal plate back here, depending on how much space we have and what the requirements are. And then the way this works, you do lose some amount of elevator extension because the gearbox and things are mounted below it, so you can't have the elevator mounted directly to the belly pan. You do have to leave a little bit of room, but it's not that much. In this case, it's a little over, what, like 2.5 inches, so nothing too bad there. Yeah, so we will go through, figure out what our actual widths are. So nothing about this is set for how wide it has to be. We can change that for our specific needs. We can make it a little skinnier or a little bit wider if we need to. We can change any of the mounting. The actual frame here might end up a little bit different depending on how we're going to mount other things to it and things. So there's a lot of different little details you can do with any of the mechanisms that we actually add onto the robot. They all get tweaked a little bit to fit the exact robot that they're going on. You never just like directly copy and paste and put something else on the robot, almost ever. You always make little bits of adjustments everywhere. Even if the overall concept is the same, you always integrate it directly into your robot. All right, I'm doing on time, cool. So that's the relatively simpler one. I guess we have enough people on that I can do continuous versus cascade real fast. So this is going to be the very quick version. I don't have a lot of diagrams, so this may not make sense, but it's fine. Anytime we talk about elevators, it's useful to know. There'll be a lot of teams using elevators this year. In a pick and place game like this, when we do have to raise up to like 6 feet and potentially a little over 7 feet for the algae, you're going to see a lot of elevators, and they can kind of be what's called rigged, whatever the belt or cable or chain that's used for the motion. We normally call that the rigging or something like that, how the elevator is rigged together. And so in this case, we have a continuous cable. We have one cable that's running through the first stage and then to the carriage. The other way you can do it is what's called a cascade elevator. And so our first loop here that we're going to build for our single stage is basically how you start a cascade elevator. You only move the first stage up and down, and that's the only thing that the motors are directly powering. And then you basically do the same thing with another loop that basically kind of almost goes around this first stage. So it either goes around the first stage, or sometimes it'll be like a chain or a belt that's on the first stage. And what you do is when it's all the way at the bottom, let me pull this down. Let me hide this belt so it's less confusing. So when it's all the way at the bottom, we have our single loop of belt that we know we can like move up and down. Since it's attached here, it's going to move it up and down. We'll have another loop of belt. It would be like maybe to the side of it, or maybe forward or backward. Sometimes it's even like down the center if you don't need anything to go through the center. Sometimes it's just like mounted to the back here. It's like a loop of cord. Sometimes it's like a nylon strap. You can use basically anything that can have that can take some amount of tension and can be put in a big loop. Will go somewhere. And one side of that loop is going to be mounted what's the easiest way to start this? So the pulleys for that loop are going to be mounted to the first stage. They're going to be mounted to like this rail and this rail. So the top and bottom of the loop are going to move with this stage. And then along that loop somewhere, say like we're going to do this on the inside here, you would have the loop fixed to this position, so it can't move at all. So however it is down here, you would like just completely connect that bit of belt or chain or string directly right here. And you would do the same thing on this side of the carriage. So you would directly connect it to this side of the carriage. And so the string itself or the loop is not connected at all to here. It's just riding over some bearings, so it can like slip across and it can move all at once along the first stage. So you can imagine as I pull this up, the string here doesn't move in relation to this rail, but now the distance between here and the pulley up at the top of this are going to be different. So this is getting longer. And so if this side of the loop is getting longer, that means the side from here down to the pulley has to get shorter. And so the carriage here has to do the same thing. It's not letting me do it very nicely. Just because Onshape moves things a little bit weirder than real life gravity does. And so as the length of string between here and here, more of it ends up on this side of the tube. That means this side is getting pulled up. And so by the time it actually reaches the top, both of these are all at the top together. And that's how the cascade one works. So you're kind of just transferring power because it's just the relative motion of this first stage that you were already moving with the motor. So you'll see some of that as we go to events. There's several different videos on YouTube that can explain the difference in cascade and continuous. If my description didn't make any sense, normally I have like graphics and things. We have some other slideshows that do that too. But you will see it throughout the year because a lot of people will have an elevator that looks pretty similar to this. There's some different types of bearing blocks and things, but they're largely become generic-ish across most of the FIRST Robotics teams. We all pretty much build them with 2x1 pretty much the same way. There's a few teams doing something different, but the vast majority of them all kind of look like this. Okay, cool. Timing's working pretty well, so we can talk about the arms. So in this robot concept, we have that elevator that's going to go up and down. I can unlock it. So this would be, maybe I can unlock it. All right. So this would be the elevator that moves up and down. And so we'd have motors down here. We'd have the belt going over this purple thing, mounted somewhere in here, so it's able to reach all the way up and give us a lot of extension. But for us to actually manipulate the game pieces, our current plan is to have something that allows us to have a joint here that's able to rotate. Let me fix the elevator so Onshape doesn't move everything. All right, so this can basically spin around. It won't be able to continuously spin. It'll have some sort of angle limits, probably something like here to here or so, maybe here. It just depends on what all the positions we need it to be able to go to, kind of determine how much room it can have. But it'll never be able to like pass 360, or all the wire management would be bad. It would wrap itself up. It might unplug things. It would be hard to know its exact position. So there will be something basically mounted inside of this frame. There'll be like a plate across here. It'll have a shaft going through it, and that's what this will be spinning on. In addition to that, we'll have a second joint. So we call this the shoulder. We're kind of modeling this like the human arm. So this is our shoulder. This is our elbow. And so this will be able to rotate as well in relation to this. So we're able to move this up and down. And the nice thing about how we do it, which I'll show on our 23.5 robot here in a second, is that what we do is it's coaxial. So both of the motors that are driving both of these two rotations are both going to be mounted down here on this stage of the elevator. So they'll go up and down with the elevator. So they stay in the same distance away from this center axle here. And so they'll have chain running up to here, and the other one will have chain running to here as well. But they'll be a little bit mounted to two different things, and I'll show you how we do that here. But it basically means one of these will directly rotate this, this motor, or this arm. The other one will basically just spin a shaft that will have another sprocket here that'll go down and spin this shaft. And because of that, because they're coaxial, like they share that axis of rotation, we're able to set this angle independently of however we set this angle. So Onshape actually does this really well. If in our software we tell this arm to go to 45 degrees, let's call this 45 degrees from like the floor, as we move our shoulder, it's going to stay at 45 degrees the whole time. So it's not like we have a motor mounted here to where like these two, if we didn't also change that motion, we don't have to like power this and know how this one's at to be able to get this to 45 degrees. We can just set this to 45 degrees from the floor, and it basically does, it stays consistent because of the way the chain are connected through these joints. It's often called a virtual 4-bar because these chain links act as a linkage that as it rotates, it actually is spinning this a little bit in relation to this arm. But it makes it much easier to control with software as that happens. So we're not having to worry about, oh, we moved this 5 degrees, that means we need to move this 5 degrees back down, or anything like that. The point of this, the reason we have these two different joints instead of just a single one, is it really allows us to get to a lot of different needed positions. You can basically set the arm and the end of the arm where we're going to grab the game objects into pretty much any position around the robot that we might want it to go to. And if for some reason we designed something a little bit wrong, we can always just tweak that position. So if for some reason, say we have a position up here somewhere that's going to score the level 3 coral, and we get to the event and we find out, oh, we're a little bit low in our level 3 coral position, the PVC is like hitting the peg instead of actually going on, we can just go into software real fast, move this up a little bit, move this up a little bit, and now our scoring position is higher, and we didn't have to redesign the robot to change any of those positions. It allows us to keep like this amount of the robot, or whatever's at the end of the arm, inside the robot more often. ignore like what these wheels are doing. They're just floating. We're playing around with different concepts. But if we can imagine the PVC pipe that we have to be able to intake slides into here, if we drive up to the human player station, we may want to make it so that our bumpers are the first thing to hit, so that we don't break or crash our arm. So like depending on how you had a single jointed arm, it may be that this is out here somewhere, and that's the position you have to get to intake, and then you can't just like drive in super fast, slam this into the wall like you can with your bumpers. So if we move it down, bring this back, so now our bumpers are the first thing to hit. The pilot's able to just drive it straight in, human player can roll it down, and now we have the coral, and we have this nice position for that. We can also do things like extend this down and potentially be able to pick up things from the floor. We can potentially rotate this, or I guess depending on how we want to do it, these wheels and these ones might go down and like pick up coral somehow from over here, or algae, sorry. Might be able to pick it up and then go take it into, and like put it up into the net if we need to. So like there might be a ball here that we're going to spit out into the algae net. So there's a lot of different positions we can play with to where we can figure out, oh, that's a little bit off. Maybe we want to be a little bit further back and then a little bit farther forward if Onshape would let me angle it. And so you have a lot of those different positions, and you don't have to worry about it. You don't have to really design it all from the beginning. You kind of have to set some of these lengths, but you can then just change your angles, change your elevator height, and get to different positions and different motions pretty quickly. So it worked really well for our off-season robot. We liked it a lot in that we could change the way we were scoring things. We even learned the robot could do things we didn't expect it to do, like kind of while it was doing it, we changed some of the motion paths and things. And so that works pretty well. So how do we actually do this, and what does it look like to actually create it? So what do the motors look like? How do the sprockets and chain and all of that work? So most of that is done by our, we're going to use a very similar system to what we used in 2023 off-season. We have that full robot CAD here. And so we've actually been doing some testing with this robot. We have it running our 2025 software. And so we're able to see it like hold coral. We changed the intake a little bit. So it's able to hold coral here. It's able to kind of score and pick algae off the reef a little bit. And so we can do some tuning on it because we already have an arm that sort of works. So we can see a few things about how it works. On this specific robot, it had this slide that would move in and out. This is sort of like our elevator this year, except it's just going to go straight up and down. So we don't have to extend out like we did that year. So it's just going to go straight up and down. And our motors here, so we have one motor here with a gearbox and a chain. And we have another motor here with a gearbox and a chain. And so these are our two gearboxes for our arm. So this one is the one that's going to power our shoulder. So if we come up here, this is the simpler one. This sprocket, as that motor turns, it's just rotating this sprocket. And these bolts that are bolting through the sprocket, bolting through this spacer, and then are bolting directly into this part. Maybe. No. There it goes. All right, so it has a part inside of here that had some threads in it and things, and that let us bolt directly to this arm. And so whenever that motor spun, this whole arm spun. And so we're able to move that up and down. It loads a little slowly. Maybe it'll load. Okay. So that one doesn't take all that much to understand. We can see that this is completely fixed and that's just bolted. The interesting part of this though is that the shaft that it's spinning on, this shaft here, it's not connected to this shaft rotationally. So it just has what we call bushings. So it's just sitting on. Nope, I did that wrong. Hold on. There we go. So it's just sitting on these bushings, and it's able to spin around this shaft. And so as this arm spins, it doesn't spin this max spline shaft at all. So this would just be what we call a dead axle. So the sprocket and the arm spin, but the shaft doesn't spin when this needs to move. Instead, this shaft is used for our elbow. And so the motor here, when it rotates, it's spinning this sprocket. And we can see if I uncover this little piece here, this sprocket has the same shape, this spline shape. It's called max spline. Rev Robotics makes it. And so this max spline shaft spins along with that sprocket. So it's kind of like a big piece of hex shaft, basically. And so this shaft is connected out to our other arm sprocket. Let me see if I can get the intake out of the way here. Maybe. There it goes. Okay. So down over here, this is connected to this sprocket. In CAD, it's not keyed directly, but all of these little bump outs are all inside these little cutouts. And so these two sprockets spin exactly together. And then this sprocket has its chain again down to this one. And in a similar way to the one up at the top, this sprocket is attached to this arm. So whenever this sprocket changes, that's the one that controls its motion. And so down on this end here, we have those bushings again, so that this shaft is able just to spin freely inside of this arm. So if you didn't do that, if you mounted these together, if you mounted these together, that would cause a problem. All right, there we go. If you mounted these together, that would cause a problem, as you wouldn't be able to spin this at all if instead of the bushings here, you had it actually like connected to all of these cutouts. So you want this to basically just act like a circle that's able to freely rotate, and then you don't want that to happen here. And so to do that, this tube has all those little max spline patterns cut out in it. And so this is how we're actually transferring that motion to the arm that has our intake on it. And so we use this to be able to get into all sorts of different intaking positions. It was able to come down. It was able to come down here and grab cubes and cones off of the floor. Oh, everything moved. All right. It was mostly able to do that. It's harder to do it in Onshape than it is in actual software. It was also able to score cubes and cones on all the levels. It was able to nicely grab cones and cubes from either of the loading stations. And so it was just very, very versatile. We didn't actually have to, part of the reason we designed this in the off season is we wanted the robot to be able to complement any of the other robots in the game, because we could just program it to do most any action. We didn't have to make any real design choices, because we could just have the arms go to different positions and they could do various tasks throughout the game. And so we think that same advantage is going to work for us very well this year. As if we're going to human load, or if we're going to potentially ground load, scoring algae or coral, all of the different tasks that you can do in this game, the elevator with the two arm joints allow us to move our grabber into any position that we need it to. What's the other part of that? So, yeah, most of it isn't too difficult. We're not having to custom make any gearboxes. We just use These gearboxes here are called Max Planetaries that we buy from Rev. The Max 90s make it easy to have them kind of compact. The sprockets and chain are very easy to get tensioned. We have inline tensioners that you're just able to like turn a few nuts and make sure the chain can never pop off and that you don't have a lot of backlash in your system. The sprockets and things are all relatively easy to acquire. There's nothing really hard to manufacture. So it's all things that we've kind of done before, and we've done pretty well. One of the things we can look at here that did happen, so one of the things we had to learn with this robot is as we played with it, so we played, as we were developing it and testing it, we found that this joint started to get a little loose. So we use snap rings here to hold the whole assembly together. And when we first put it together, it was actually pretty hard to get this snap ring in. We basically had to clamp these two sprockets together so that we could get the sprocket down below this groove line here to actually be able to put the snap ring in. And so that meant the whole system was very tight. It wasn't wiggling much at all. Like you couldn't move this arm side to side. It would only rotate like we wanted it to. But because part of this is plastic, we had a plastic 3D printed part here. Same with these pieces. These were polycarbonate. No, actually, I take it back. These were aluminum. These are 1/4 inch aluminum. But we did have some plastic here. We had some plastic spacers. As it compressed and we used it, it's starting to loosen up a little bit. And so before we went to one of our first events, it was getting pretty shaky. And we were worried that it was going to make it so it was hard to control because you didn't necessarily always know where the end of your arm was. Because if this starts shaking, the end of your arm will start shaking as well, and you may not be able to score the object, right? We might be a little too far left or right to be able to put the coral on the branch. So to counteract that, we made this system here. So this end cap is a relatively simple part. This is just 3D printed. It's basically just a flat plate here, has a ring, and then it just has this internal cavity. It has a hole for a bolt. And so we put a bolt through this into this piece of hex shaft that's a little bit shorter than the whole max spline shaft that it's inside of. And then on this far end, we have this little spacer built that would make the hex shaft stay in the center of the max spline shaft. And we would put a bolt and a washer here so that this end of the hex shaft couldn't be pulled any further into this max spline shaft. So we wanted these ends to stay together. And then as we go ahead and turn our bolt inside of here, since we're not touching, hold on. I do wrong. Okay, so since we're not touching any of this snap ring, this max spline, or this hex shaft with that outer part, we're only touching the sprocket. What that lets us do is it basically lets us push this sprocket closer to the end of this max spline shaft because we're kind of pulling this whole assembly in this direction. And so that took up all of that little bit of slop and play that had built up in this connection. And it held up very well for the competitions. If at any point we saw it getting a little bit loose, we were able to just turn that screw a little bit more, and you can apply tension to it. It allowed us to almost act as a bit of a friction brake, because as you squeeze this all together, it makes it so the arm doesn't want to rotate as easily since it's all getting compressed together and has a little bit more friction. So you could choose how much friction was on those sprockets. And that helped keep it in position. It allowed us to have very easy and smooth position control because you're able to just kind of adjust that as you need to make the system work well. This is very likely something that we're going to do again. There's some talk of potentially modifying it so that we can still run wires through this tube possibly. So if you can get a little hole here somewhere, you could run wires through it. or through the edge of the match spline shaft somewhere, so you could actually have the wires come out inside the match spline shaft possibly. So there's a lot of different options we could do there. If we need to, though, we can just we can run them through the outside like we did before. That's totally fine. Similarly, through this tube, we did run the wire. For this one, we ran it inside the tube. I think there's a hole here. So we ran the wires up inside this tube. So it didn't get caught anywhere, because you don't want to have the wires getting caught on any of these chains, getting cut, getting damaged. So wire management is always an important thought as we're building any of our moving systems. We want to be careful that we can keep the wires intact. And then from there, the wires move into here, and they went through this joint here, and then out to our motor that was positioned right here to control the intake. So some of our normal control things are that we, and kind of just the base concepts for what we're trying to do. So some of the base concepts of what we're trying to do are to be able to move our weight a little bit lower, and you almost always want your weight towards any of your pivots. So in this robot here, since we know we're going to have a couple motors here to control the arms, we're going to put those pretty low as we can on this carriage. And so when we go to rise up, we're not moving that weight higher than we need to. Similarly, we may have motors out here that may twist this wrist this year. We may be able to swing this around. So that motor may be mounted back here towards our elbow joint. But because this is twisting, the motor that actually spins these wheels will probably have to be past the twisted joint, so we're not having to transfer the motion through the twist. It's a little bit harder to do that since it's not the same plane as this twist is going in. But in general, we're always trying to keep things pretty clean. We don't want any wires to get caught on anything. We want to keep our weight low. There should be some motions that we can do with a relatively low elevator so that this whole mass is able to stay relatively smooth and low. We are also, one of the other advantages here is that you're able to do all the motions at the same time. So we're able to, like if we need to go up to score on the top branch of the reef, we're able to raise the elevator, raise the arms, and get them all into position kind of simultaneously. And so that helps you go a little bit faster as you can kind of get ready for whatever that motion is as it's happening. And you sort of gain height together as we can be both moving the elevator up and swinging this arm up at the same time. So you're just a little bit quicker going all the way up. I think that's most of what I wanted to cover tonight. I don't think there's any other part of this that's too different. There are some times where we can choose between bushings, which are basically this part right here is is normally made from a impregnated oil infused metal. So a lot of times it's bronze. And so as you kind of give friction, it lubricates itself so it can spin freely. The other option is to actually use ball bearings, similar to like the hex bearings we use on a lot of things. They're just a little bit bigger, so we may have to have some parts that hold them to the outside, depending on how much we want the stack up to be, for how like wide we want this assembly to be. So you may end up needing a little bit more room here if you have to have bearings on either side of this. Similarly, we may need to add like a similar tension mechanism like we have up at the top to the elbow here so that we can keep this joint solid as well. You do have chain tensioners on all three of these chains that reduce some of the backlash. We also do some backlash reduction inside of our max 90 gearboxes to make sure that these are spinning nicely, including like the hex shaft that goes inside of them. It doesn't have any twist, can't twist without the actual motion of the motor, because one of the goals is that we only want the system to move if the motor is actually telling it to. We don't want there to be any little bit of wiggle or wobble or anything like that, so that when we tell the robot to go to the same position every time to score our game pieces, they actually do that. I think that's most everything. Thank you all.